I spent my career at Cambridge studying black holes, objects where gravity is so extreme that not even light can escape their pull. And in doing so, I made a discovery I never expected, and if I am honest, initially wished were wrong. Black holes radiate. They lose mass particle by particle, and over unimaginable timescales they evaporate entirely, vanishing from the universe in a final burst of energy. That discovery unsettled me because it carried a weight I had not anticipated. If even black holes are temporary, the most durable and most gravitationally powerful structures in all of nature, then nothing is permanent. Nothing at all. And once you accept that, one question becomes unavoidable. How does it all end? Not just your life, or our sun, or our galaxy, but everything. The answer is stranger than you imagine, and it is also more beautiful, and it begins, as so many things in physics do, with Albert Einstein. In 1915, Einstein published his general theory of relativity, which replaced Newton's idea of gravity as a force with something far more radical. Gravity, in Einstein's framework, is the curvature of space-time itself. Mass tells space-time how to curve, and curved space-time tells matter how to move. The equations were elegant, but they were also troubling, because every solution Einstein found implied that the universe must be either expanding or contracting. He found this so distasteful that he introduced an extra term called the cosmological constant, a kind of repulsive energy woven into the fabric of space, purely to hold the cosmos still. He later called it his greatest blunder, and that is one of the great ironies in the history of science, because he may have been right the first time. That part of the story comes later. What matters here is that Einstein's equations predicted a universe with a history, and in the late 1920s, Edwin Hubble confirmed it. The galaxies are moving apart, which means the universe is expanding. Run the film backwards and everything converges toward a single point of unimaginable density and temperature. In the late 1960s, Roger Penrose and I proved a series of mathematical theorems showing that, under very general conditions, general relativity predicts its own breakdown. A singularity forms, a point where density becomes infinite, and the known laws of physics cease to apply. This was the Big Bang, not an explosion in space, because there was no space for it to explode in, but the origin of space and time themselves. To ask what happened before the Big Bang is, as I have often said, rather like asking what is south of the South Pole, because the framework you need to pose the question did not yet exist. Working with James Hartle, I took this further. We propose that the universe has no boundary in imaginary time, no edge, no starting point, no moment of creation requiring explanation. The universe simply is a self-contained geometry that is finite but without a boundary, like the surface of the earth but in 4 dimensions. This is the no-boundary proposal, and it suggests something about the relationship between the beginning and the end of the cosmos that nobody had suspected. They may be more deeply connected than anyone realized, and that is where nature played its greatest trick. For decades, the central question in cosmology was simple enough to state. The universe is expanding, gravity is pulling everything back together, and the question was, which force wins? If there is enough matter in the cosmos, gravity eventually halts the expansion and reverses it, collapsing everything into a big crunch, a singularity at the end of time that mirrors the one at the beginning. Too little matter, and the expansion continues forever, slowing down but never quite stopping. Measure the density of the universe, compare it to the critical value, and you know the fate of everything. It seems straightforward, but in 1998, 2 teams of astronomers shattered that assumption. One team was led by Saul Perlmutter, the other by Brian Schmidt and Adam Rees, and they used type Ia supernovae as standard candles to gauge cosmic distances. They expected to find the expansion slowing down, and what they found instead earned them the Nobel Prize and overturned everything. The expansion is accelerating. The universe is not merely growing, it is growing faster with every passing moment, because something is pushing the cosmos apart, and it is winning. We call this dark energy, and I will be candid about the fact that we understand almost nothing about it. Dark energy appears to be a property of empty space itself, where every cubic meter of vacuum contains a small amount of energy. As space expands, more space is created, which means more energy, which drives further expansion. Einstein's cosmological constant, the term he introduced and then regretted, turns out to describe something real. But here is what should disturb you. When physicists attempt to calculate the expected energy of the vacuum using quantum field theory, the answer disagrees with observation by a factor of 10 to the power of 120. That is not a small error. That is the single worst prediction in the history of science. We know dark energy exists because we can see its effects, but we cannot explain why it has the value it does, rather than a value that would have blown the universe apart in the first fraction of a second. This is not a minor puzzle, but a chasm at the foundations of physics. The first consequence of accelerating expansion is isolation. As space stretches, distant galaxies recede from us faster and faster, and within roughly 100 billion years, every galaxy beyond our local group, the Milky Way, Andromeda, and their small retinue of companions, will have crossed a threshold. The space between us and them will be expanding faster than light can traverse it, which means they will not merely be far away but fundamentally unreachable. Their light will never arrive, and one by one they will redshift beyond detection and vanish from the observable universe entirely. Think about what that means for the future of knowledge. A civilization arising 1 trillion years from now, in whatever galaxy has formed from the merger of the Milky Way and Andromeda, would look up at the sky and see nothing. No other galaxies, no cosmic microwave background, because it will have redshifted into undetectability, and no evidence of the Big Bang whatsoever. They would conclude, perfectly reasonably and completely wrongly, that their galaxy is the entire universe, static and eternal. The greatest discovery in the history of cosmology would have been erased by the very expansion it describes. The universe does not merely die, it destroys the evidence that it ever lived. But the disappearance of galaxies is merely the opening act. Stars are not eternal either, because they survive by burning nuclear fuel, converting hydrogen into helium, helium into carbon, and so on up the periodic table until the fuel runs out. The most massive stars burn ferociously and die young, detonating as supernovae in spectacular displays of nucleosynthesis. Medium-sized stars like our Sun burn more steadily, lasting billions of years before swelling into red giants and collapsing into white dwarfs. Those dense Earth-sized remnants that slowly radiate away their remaining heat. The smallest stars, the red dwarfs, are the misers of the cosmos, sipping their fuel so frugally that they can persist for trillions of years. But even red dwarfs must eventually go dark. By roughly 100 trillion years from now, 10 to the 14th power, the last star in the universe will have exhausted its fuel. This is the end of what astronomers call the stelliferous era, the age of stars. It happens to be the era we are living in, and it is extraordinarily brief by the standards of what follows. Once the last star goes out, no new ones will form, because the raw material, gas clouds dense enough to undergo gravitational collapse, will have been consumed or dispersed beyond recovery. From that point forward, the universe will be dark, but it will not be empty, not yet. What remains is a cosmos populated by stellar corpses, white dwarfs cooling toward absolute zero, neutron stars spinning down over the aeons, and black holes, particularly the supermassive black holes at the centers of galaxies that will have grown enormously during the stelliferous era by consuming stars and gas in each other. And this is where my own work takes center stage. In the early 1970s, my colleague Jacob Bekenstein proposed something radical, the idea that black holes possess entropy and that they must have a temperature. I initially resisted this because if a black hole has a temperature, it must radiate, and if it radiates, it loses energy, and if it loses energy, it shrinks. A shrinking black hole contradicts everything general relativity appeared to tell us about the permanence of event horizons. But when I applied quantum field theory to the curved space-time near a black hole's event horizon, the mathematics was unambiguous. Bekenstein was right, and the consequences were staggering. In the vacuum of space, quantum mechanics demands that pairs of virtual particles are constantly flickering in and out of existence, appearing and interacting and annihilating so quickly that they seem to violate conservation of energy, shielded by the uncertainty principle. Near the event horizon of a black hole, something extraordinary happens. One particle of such a pair can fall through the horizon while the other escapes, and the escaping particle carries energy away. Because energy and mass are equivalent, as Einstein showed, the black hole loses mass. Particle by particle, it shrinks and evaporates. Let me say that again because it deserves emphasis. Black holes evaporate. The most gravitationally powerful objects in the universe, from which not even light escapes, are dissolving, slowly, imperceptibly, but inevitably, into radiation. The process is spectacularly slow. A black hole with the mass of our sun has a temperature of roughly a 10 millionth of a degree above absolute zero, far colder than the current cosmic microwave background. Right now, a black hole of that size actually absorbs more energy from its surroundings than it emits. But remember that we are discussing the far future, when the background radiation has cooled to effectively nothing. In that frigid, dark cosmos, evaporation will proceed unopposed, and a solar mass black hole would take approximately 10 to the 67th years to disappear entirely. The supermassive black holes, the ones weighing billions of solar masses, require something on the order of 10 to the 100th years, a Google years. To grasp how long that is, the current age of the universe, 13.8 billion years, compares to a Google, the way a single atom compares to the entire observable cosmos. The analogy fails because nothing in human experience is adequate. And as a black hole shrinks, something counterintuitive happens. It gets hotter. Temperature is inversely proportional to mass, which means the smaller it becomes, the more furiously it radiates. In its final moments, it reaches extraordinary temperatures in what might fairly be called an explosion, and then it is gone, entirely gone. This raises what I consider one of the deepest problems in all of physics, the information paradox. When matter falls into a black hole and the black hole subsequently evaporates, what becomes of the information that described that matter? Quantum mechanics is built on a foundational principle that information is never truly destroyed, because the evolution of any quantum system is in principle reversible. But the radiation I showed black holes emit appeared to be perfectly thermal, perfectly random, carrying no trace of what fell in. If that is correct, then black hole evaporation violates the most fundamental principle of quantum mechanics. In 1997, I made a bet with John Preskill and Kip Thorne. Preskill wagered that information must be preserved, and I wagered it was lost, that quantum mechanics at this extreme must yield. I have since conceded that bet, and I now believe information is preserved, encoded in subtle correlations in the radiation. But the precise mechanism requires a complete theory of quantum gravity, a unification of general relativity and quantum mechanics, which remains the great unfinished project of theoretical physics. Whether it takes the form of string theory, M theory, loop quantum gravity, or something not yet imagined, I believe that theory, when we achieve it, will illuminate not only black holes but the deepest structure of space-time itself. There is one more catastrophe worth describing before the final darkness. Between the death of the last star and the evaporation of the last black hole, there exists an open question about the stability of matter itself. Grand unified theories, which attempt to merge the strong, weak, and electromagnetic forces, predict that protons may not be eternal and that they may decay with a half-life on the order of 10 to the 40th years or longer. If proton decay occurs, then every atom in the universe will eventually dissolve, and white dwarfs, neutron stars, planets, and dust will slowly disintegrate into a thin haze of leptons and photons. Matter itself is temporary. After the last black hole has evaporated, after matter itself has perhaps dissolved, what remains is a universe of extraordinary desolation. Photons, neutrinos, and possibly a dilute gas of electrons and positrons, all drifting ever farther apart in the expanding void. The temperature of the universe will approach, but never quite reach, absolute zero. And this is what physicists call the heat death, the state of maximum entropy and maximum disorder, in which no further work can be done, no structures can form, no computation can occur, and no complexity can arise. Nothing happens, and nothing can happen. The game is over, not because anyone won, but because there are no possible moves left to make. There are alternatives that might spare us this particular ending, or replace it with something equally strange. If dark energy is not constant, but instead grows with time, it could eventually overpower not only gravity, but the nuclear and electromagnetic forces that hold atoms together. This is the Big Rip, a scenario in which the universe tears itself apart at every scale, from galaxy clusters down to atomic nuclei, in a finite time. And then there is what I find the most unsettling possibility of all. The quantum fields that pervade the universe may not be in their lowest energy state, and instead they may be metastable, balanced like a ball resting in a shallow dip atop a hill rather than in the valley below. A quantum fluctuation could nudge the field over the edge, triggering a phase transition, a bubble of true vacuum expanding outward at the speed of light and rewriting the laws of physics in its wake. Everything in its path, matter, energy, the structure of space-time, would be transformed into something entirely different. And because the wall of transformation travels at the speed of light, it arrives at the same moment as the first signal of its approach. There is no warning, and there is no escape. One moment the laws of nature are as you know them, the next moment they are not. I mention this not to frighten anyone, but because it illustrates something about the relationship between physics and philosophy. The universe is under no obligation to be comprehensible, and it is certainly under no obligation to be kind. It was not designed for us because it was not designed at all. The same laws that permit the astonishing complexity of living beings, beings capable of sitting at desks in Cambridge and calculating the terms of their own extinction, also guarantee that all of it is temporary. Every structure the cosmos builds, it will eventually unmake. And yet I have never found this cause for despair, quite the contrary. I have lived most of my life with a motor neurone disease that was supposed to kill me before I turned 25, so I am familiar with the prospect of endings. What I have learned, both from my own experience and from the equations, is that finitude is not the enemy of meaning, but its source. If the universe lasted forever and nothing ever changed, there would be no arrow of time, no evolution, no thought. It is precisely because the cosmos runs down, because entropy increases, because stars burn out, because black holes evaporate, that anything interesting happens at all. Complexity exists in the gap between the initial low entropy of the Big Bang and the final high entropy of the heat death. We live in that gap, and in a real sense we are that gap, briefly organized into something that can look back at the whole process and understand it. In my final work with Thomas Hertog, I argued that we should not think of the universe as having a single predetermined history stretching from the Big Bang to the heat death. The no-boundary proposal, combined with quantum mechanics, suggests that the universe has many possible histories and that we select among them by the observations we make in the present. The past, in a certain quantum mechanical sense, is not fully determined. This is top-down cosmology, the idea that the universe does not have a history independent of the questions we ask of it. If that is correct, then the end of the universe is not a destination written in stone, but the consequence of laws we are still in the process of discovering, and the story is not finished as long as someone is still working on the equations. The stars will go out, the black holes will evaporate, and the last particles will drift apart in the expanding dark. That much is as certain as anything in physics can be. But the fact that we know this, that we, improbable arrangements of matter on a small planet orbiting an ordinary star, have taken the measure of the entire cosmos and calculated its fate, that is not a footnote in the story. That is the whole point of the story. Not the duration of the light, but the fact that the light was there at all.